If we zoom in a silicon piece, we see that every silicon atom has four covalent bonds with four adjacent silicon atoms. And therefore, we wouldn't have any free electron, since it has four electrons in its last shell or in the valence shell, and all of them are contributing in four covalent bonds. But this only happens at the absolute zero. When the temperature rises, the number of free electrons would exceed based on this equation, which T obviously is the temperature, and E of G is the band gap energy, which somehow means the energy required for an electron to break out of the bond. If we put 1.12 for the silicon, 1.12 electron volt for the silicon, and solve for this at room temperature, we see that the number of free electrons in 1 cubic centimeter would be equal to 10 to the power of 10. So as the temperature rises, these electrons would break out of the bond. As an example here, you see that one electron has break out and therefore is a free charge. But in the covalent bond, now we have one electron. It's not full. It's like we have a hole there, something to make some space for another electron to fill that bond. To explain the concept of holes, I want to use this analogy. Imagine that we have some soil here and we have a hole. Now, imagine that someone here would dig another hole with a shovel and pour the soil here into this hole. So here, the soil would be here. We don't have any hole here anymore, but we would have a new hole here. Then would go to the next place and would do the same thing. With shovel, would dig the hole out and inside this hole. So we don't have a hole here, but we have a new hole in this place, and would do the same thing. It's like that even though the soil is moving to the right, but we could use an abstraction and say that one hole is moving to the left. Now, why would we use such an abstraction? First of all, we don't know the exact value of the soil. We are just moving it with some shovel. Second, it's many part of the soils, one part here, then another here, then another here. But using this abstraction, we are just abstracting all of it using just one hole. The direction just changes. Now in here, the same thing happens. We could say that if we have a place here, if the temperature rises when the free charge, one free electron we have here, actually let me use another example so it's more free. So imagine here one electron has break out and we have a hole in this place. As the temperature rises, other electrons in the nearby would get the thermal energy, would break out here, but then would go in this hole and make a bond with this electron and would fill that bond. But then in here we would have a new hole. And then another electron in the adjacent atoms would again, because of the temperature rising, would break out of the bond, would fill this covalent bond, but would leave a hole here. In fact, for any electron that it only makes sense that for any electron that is breaking out of its bond, it would leave one hole. So instead of, first of all, this electron that breaks out is contributing to the current if we put some voltage. Actually, first of all, let me say this. If we have free charges, right now they have random motion as the temperature rises. But if we put a positive voltage, let me use another image. Let's say that we put a positive voltage at this side with respect to the other side. Now electrons, these free electrons, would move to the positive side. Other than these free electrons that would contribute to the current, for any electron, it leaves one hole. And even though the adjacent electrons here, like when we have provided the positive voltage here, in this case, this electron here would get some energy and would fill this bond, therefore leaving a hole here. Another electron here would get the energy, would fill this bond and leave another hole here. As you see, the electron always moves to the positive side of the battery, but it leaves one hole behind. You see, even though electrons are moving to the right, but we could abstract it as if one hole is moving to the left. So I want to summarize this because this is a very important concept to understand what comes next. You see, for any electron that breaks out of the bond, it leaves one hole. First of all, those free charges would contribute to current. Now, put that aside. For the hole that remains, even though some other electrons in the adjacent atoms would move and fill that hole. But just like the soil example, instead of all those electrons moving to the right, we make an abstraction and we say it's like the hole is moving to the left. So it's not that we say hole, we either look at the current as the movement of the holes or electrons. We say both electrons and holes are contributing to the current. The free electrons would contribute to the current. This is one part. Also, the holes are contributing to the current, the holes in here, even though those holes are the result of the adjacent electrons moving to those holes, but we make the abstraction. We say other than free electrons that are moving, we also have some equal number of free holes that they would also contributing to the current. And obviously, if electron moves in one direction and holes move to the other direction, it just means that both of them are contributing to the current in the same direction, because holes moving to the left just means some electrons are moving to the right. Those electrons plus the free electrons contributing are in the same direction, therefore they would both contribute to the current. So there is one, just imagine the analogy of the soil and the worker and everything would make sense. I just don't want you to confuse the free electrons with these electrons that would break out, that we have abstracted it as the holes. If we give the numbers and work out the numbers using the equation of the Ni that I told you is the number of free electrons in 1 cubic centimeter, by putting the value of 300 Kelvin and 1.12 for the E of G, we get the number of 10 to the power of 10. That would be the number of electrons. But I just explained, for every electron that gets free out of a covalent bond, it leaves behind one hole. So we expect to have the same number of holes as well. Sometimes we show free electrons as N and free holes as P. It is obvious that if N and P are both the same, which is equal to Ni, then we could say Np is equal to Ni squared. Even though these wouldn't be important for us, as this is not a physics of electron course, but rather it is, we just want to make a switch. As you see, the goal of all of these things is to make a switch, and these are the requirements to understand how we make a switch. So far, the summary of everything that we said was just that we have a silicon piece, a pure silicon or intrinsic silicon, and we saw at the room temperature the electrons in the covalent bonds would break out of their bonds and therefore would get free. Why do we need free electrons? To have current. These have been explained before. When we have free electrons, we would have the same number of free holes as well. Then we could direct those free charges by putting a voltage at both sides. But the problem is that this number of free charges is a small number. 10 to the power of 10 is a small number to have a reasonable current. So we need to increase these number of free charges. One way, as you saw, was to increase the temperature. We need another way to increase the number of free charges. This would be both increasing the electrons or increasing the free electrons or increasing the free holes. And we'll see that we would use a method called doping in the next lecture.